Question 9. Here we're asked to state what distribution represents this situation where Sue throws a fair coin 15 times and records the number of heads. So we've either got heads or tails, so we've got exactly two possible outcomes, so binomial distribution seems appropriate, and the number of throws is fixed at 15. So we've got a binomial distribution, n is 15, the number of throws is 15. Now the probability of success, the success being a head in this case, probability of the head then is 0.5. And so that is going to be our distribution. Part B, here we're looking for the probability that x equals 8, given the distribution, it's a binomial with a probability of success of 0.5. So what I'm going to do is go back to my calculator here and change these values. So this time x equals 8, n value is 15, probability of success is 0.5. So x value we're interested in is 8, n value is 15, probability of success 0.5, and we're in the binomial probability screen there rather than the cumulative screen. And so there we have it, 0.1964 to 4 decimal places. In part C, then we're asked to find the probability of at least 4 heads. Now, at least is 4 or more, so greater than or equal to 4 there. Now, if it's greater than or equal to, it's kind of the wrong way around to help us use the booklet. So we need to flip it around and do a 1 minus. Probability that x is less than or equal to something. Well, 4, 5, 6, etc. is what we are allowed. So therefore 3, 2, 1, etc. is what we're not allowed. So less than or equal to 3. It's cumulative probability, 15 and 0.5. Nice clean values which will appear in the formula booklet then. So if you bring up the formula booklet, n value is 15 there. Go right to the last column, which is the 0.5 column. And what we're interested in again, less than or equal to 3. So go to the row for 3, down, and we see it's 0.0176. 0.0176. Okay, and 1 minus that is going to be 0.9824. Okay, in part D, we've got a hypothesis test, still based on the same distribution of 15, 0.5 there. Now, in this particular hypothesis test, Sue believes the coin is biased in favour of heads. So that means that it's a one-tail test where she thinks that it's only that she's getting more heads than she expected is the point of interest. So in terms of our hypotheses, the null hypothesis then is always what the default was. So the default was 0.5, so p equals 0.5 still according to the null hypothesis. But the alternative hypothesis that Sue is potentially trying to prove here is that the probability of getting ahead is now more than the 0.5, which was the sort of default. Okay, she thinks it's biased in favour of heads, so p is not greater than 0.5. Now, when she does the experiment, she gets 13 heads. So that is to say, she gets 13. Now, whilst it's tempting to work out the probability that x equals 13, what we really need to look for there is the region for where it's 13 or more. Probability that x equals 13 itself would be very small. Probability that x equals 7 would be quite small, but even though it's close to the middle of the distribution. Anyway, we're looking for the probability that x is greater than or equal to 13 in this situation. Now, greater than or equal to is the wrong way around for us, so we flip it around, make it less than or equal to 12, so that then we can go to our formula booklet. N equals 15, go to the row for 12, The last column is the one with 0.5 in it, so that's 0.9963. Okay, 1 minus 0.9963 is going to be 0.0037. Now, the significance level here is 1%. 1% significance level as a decimal then is 0.01. Now 0.0037 is even less than 0.01. Okay, and because it's less than 0.01, it's so unlikely to have happened by random chance that we can say, based on the significance level, it didn't happen by random chance, and therefore we think there was something fundamentally different. Hence, we reject the null hypothesis, and we say that there is sufficient evidence at a 1% significance level to support Sue's claim that the coin is biased in favour of heads.